Okay, as you probably know by now watching my machine videos that my lathe control board went out on me, and being that this is a 7 by 10 lathe, I can't get the control board anymore because the lathe is outdated. And so in order for me to continue working with my lathe, I need to make my own control board for it. And that's what I'm doing over here in my electronics now. I'm doing some experimenting. I'm trying to come up with a simple circuit that I could build that would allow me to control the torque of the motor. In other words, whenever I use my lathe, I need to turn it to a slow speed, a proper slow speed that's necessary to do proper machining on a part. I can't have it too excessive speed or I'm not going to get proper machining on the part. And so I have to have it at a specific proper speed, but at the same time I have to be able to, whenever I machine a part on it, I don't want the motor to bog down. And that's the whole key for the motor to continue to run at that speed in a constant way, in order, like a speed control, in order to keep the machining running smooth on the part. And so that's what I'm doing here, is I'm going to make my own control circuit, my own control board for torque control, and it's not going to be running perfectly. I realize that because this is just a hobby project, but it's going to, I think it's going to be good enough to be able to do something with my lathe to make it work properly enough to be able to use it. So what I have right now, first of all, before I can even build a main circuit for that lathe, I have to experiment and come up with my own version of a torque control. Just doing some experimenting here, and this is just going to be an electronics video project. This is going to be. Okay, well, what's coming up next now will be the steps I'm taking now to build a prototype, and the experimenting to find out how I can make a control board for my lathe. And that's what's coming up next. Okay, I probably should add that I realize that the professional control boards that come with these machines, they are what they call pulse width modulation. I realize that. I'm not going to go that route with pulse width modulation, though. I'm just going to go with more or less like a voltage regulator type thing, where it's just going to be feedback from the motor stall. And I'm going to load this on the motor and have that feedback into a voltage regulator type situation. That's pretty much what all it's going to be. Okay, that's the prototype of this now, the work of this now is coming up next. And now the first thing I want to do here is I want to check and see how much current that my circuit's going to have to handle. I decided I want to run this motor with 5 volts dropped across it. I have my power supply on, and I adjusted my power supply until I get about 5 volts across the motor. Now I am reading the voltage across the motor, not the voltage coming out of the power supply, but I got a lot of wiring going on here, so there's going to be some resistance there in voltage drop. So I'm checking the voltage across the motor terminals only. And now what I'm going to do is I'm going to stall the motor to a complete stop, and I'm going to check the voltage drop across there, 4.7 volts. So I will record that now, 4.7 volts, 4.77 volts, and that's with the motor stalled. Okay, now the next step would be to check the resistance across the motor. I have my multimeter set up on ohms, and I'll now put the across the terminals from the motor terminals, and I'm getting 33 ohms. I'll record that now. Okay, that's 33 ohms. Okay, now I'll solve for the current, and this will be the surge current or the stall current, and this will be the maximum current that will be going through this motor under a stall condition. Okay, 4.77 volts divided by the 33 ohms, and that's 144 milliamps under the conditions of a 5 volts being applied across the motor and in the stall. Now what I'll do is I'll double that there just for a safety factor. That'd be 288, and just make it a nominal 300 milliamps. I'll design the circuit for 300 milliamps. Okay, so now that I have that data written down, I can now go to my design books here. This is my circuit design books here, and we're going to design a transistor voltage regulator. and I want to design a series feedback regulator. And that would be this one right here. And I will follow their instructions here. I'll follow their design procedures here, the formulas that they give. And that will be right here for the feedback regulator. Okay, we'll go through these here formulas here, and we'll apply that, and we'll build a feedback regulator as a starter for this, and then I will add on my circuitry to it to make it work as a torque converter. So right now we're going to design a feedback regulator. Okay, the first thing would be to look for the supply voltage that would be necessary to put the series pass transistor into a linear mode. Since I want 5 volts to be the output voltage, the difference in voltage for output voltage to supply voltage, okay, if that difference is greater, that puts the series pass transistor in a linear mode, and that's what we want. The higher the output voltage is closer to the supply voltage feeding it on a regulator, the less linearity you have with the series pass transistor, and because of that you're not going to have the regulation that's required. So it's best to put maybe about 5 volts or so difference. So if I'm using 5 volts for my output voltage, I want a supply voltage about 10 volts. They say that you can go, let me look at this here. They specify that a minimum of 2 to 3 volts should be, your output voltage should be at a minimum 2 to 3 volts lower than a supply voltage. Like I said, the more supply voltage you have with respect to the output voltage, the better you're going to have a regulator working due to the linearity. So I'm going to put 5 volts, like I said, across my transistor to put that in the linear region. And so now we want to solve for the resistor values, and let me just draw up the regulator here now and show how I'm going to come about this. Okay, let me give a little explanation here of how the voltage regulator is designed. First of all, we have the supply voltage coming in. This is usually unregulated. In my case, I want 10 volts coming in as a voltage in. Then you have your series pass transistor. I'm going to use an NPN. The collector goes to the 10 volt supply. The base will have a resistor, a base resistance. That's your current limiting resistor. That's always used to bias the transistor. And then we have out the output of the transistor, out the emitter will be the output voltage. And we want to add 5 volts. Now, to make that run properly, if we were to just bias it that way there, the transistor would be in saturation and you would have close to almost 10 volts on the output matching the input, pretty close. So we have to have a feedback. That means that there's going to be a sampling voltage. And what we use is we use another transistor here at NPN that has its emitter connected to a Zener diode or any kind of a reference voltage. The closer this reference voltage is to the output voltage, the better you're going to have regulation. This NPN transistor now has its base bias connected to the output as well. So there's a feedback that's happening here, is that there's a reference voltage being set up at the emitter here. That reference voltage then is compared to the output voltage here. And if there's any change in the output voltage, this transistor is going to sense that, and it's going to conduct either more or less current to the base of the series transistor, causing that transistor to turn on more or turn off to keep the voltage at an equilibrium. Now I'll explain here how we get the values with the formulas that they give. We have 3 currents that we're looking at. We have a given output current that we are designing this for. We have a base current that is the supply resistor to the series pass transistor here, and we have a divider current that biases the feedback transistor here. Now, according to their formulas, because the series pass transistor is usually a power transistor, the beta is usually around minimum around 20. So they use that as 20 minimum beta. And so the way they look at it is that if you take the output current and you divide that by 20, you can pretty much use that to be the base current flowing through this resistor here. They want the base current to be a little bit less than that, but I'm just going to use 20 just for starters. So if I take my output current, as we said, was 300 milliamps, and I divide that by 20, then that's going to give me this current flowing through here. And then we'll solve for that resistance value. Okay, that 300 milliamps divided by 20 gives us 15 milliamps of base current. I'm going to go conventional current. 15 milliamps of base current. 15 milliamps of base current flowing through this resistor here, this bias resistor here for there. All right. What we're going to do now is, for the divider current, they say a good rule of thumb is to take the base current now and divide that by 2, and that would give us 7.5 milliamps. 7.5 milliamps then will flow through the divider here, the voltage divider. Now we want to solve for this here series resistance here that's connected to the base here, and we take the supply voltage, we subtract the output voltage, then we subtract 0.7 volts, which is the base emitter voltage, from here to here. So that'd be 10 minus 5 minus 0.7, and that will give us the voltage drop across this resistor. Then we take that voltage drop and divide that by the 15 milliamps base current here, and that will give us this resistance value here. Okay, so now we have our 10 volts minus 5 volts minus 0.7 gives us 4.3 volts dropped across this resistance. 4.3 volts divided by our 15 milliamps gives us 286 ohms. We can make that 270 ohms because that's a nominal resistor value. So we will make that 270 ohms for the base resistor for the series pass transistor. Now we're going to solve for the two resistors in the voltage divider here. I have available here 3 volt Zeners. I have 5 volts and 12 volts, but I do have 3 volt Zeners, and that's below the output voltage of 5 volts. I can use these Zeners here. So I will use my reference voltage as 3 volts, and that will be my Zener voltage here of 3 volts. Now I have a base emitter resistance here, or a voltage here of 0.7 volts for the base emitter voltage. So I now have 3 plus 0.7 gives me 3.7 volts at the junction here. I have a divider current of 7.5 milliamps. So if I take 3.7 volts divided by 7.5 milliamps, that will give me this resistor value here. Give me 493 ohms. I'll make that 470 ohms nominal resistor. Now I'll take that 3.7 divided by that 470 to give me the current, which is about 7 milliamps. Okay. Now I take that 7 milliamps and I divide that into the output voltage minus 3.7 to give me this resistor value. So I take 1 over that times 5 minus 3.7, and that will give me 165 ohms. A nominal value would be 160 ohms. So the voltage divider now will have 160 ohms supply to base. From ground to base, 470 ohms. The base resistor here is 270 ohms, and the Zener will be 3 volt Zener. Let's build this and see how we regulate with this. Okay, now the first thing I need to do before I build this is I need to figure out the wattage. So we have here 10 volts, 5 volts output, 10 volts input. That's 5 volts dropped across this transistor. We want 300 milliamps flowing through there. So we take our 5 volts divided by our 300 milliamps. That gives me 5 volts divided by 300 milliamps. That gives me about 16, not divided, 5 volts times 300 milliamps. That gives me 1.5 watts. All right. So we have the voltage across there times the current flowing through there. It gives me about 1.5 watts. Therefore, a 2N3904 transistor is about 600 some milliwatts, so I can't use that. I can use a tip 41C transistor that handles about 6 amps of current. It has a good high wattage also, of course. Therefore, I can use a tip 41C for the output transistor. And let's see what the wattage would be for the for the feedback transistor now. We have 5.7 volts that would be sitting at the base here, which is connected to the collector here, and 3 volts here. That's 2.7 volts dropped across this transistor here. And we're going to have a current of about possibly 15 milliamps. Let's take a look at that. Okay, if I take the 2.7 volts that's being dropped across here, and if I were to take that times a current of 100 milliamps, just for figuring this out, I still end up only with 270 milliwatts of power. And these can handle up to 600 milliwatts, so we're within range. There's not going to take no 100 milliamps flowing through there. So therefore, I know that this can be a 2N3904 transistor because we're within about 300 milliwatts, and that's under 100 milliamps of current flowing. So we should be good there. And now I need to figure out the wattage of the resistors now. And that would be, this would be 15 milliamps squared times 270 ohms. Let's check that out. That resistor is 60 milliwatts. Let's check this one here now. 470 ohms times 7.5 milliamps squared. Comes out to 26 milliwatts, so we're fine here. The 160 ohms is even smaller, so that's fine. So then we know then that this can be a quarter watt resistor, another quarter watt resistor, and this right here again, I think that was a quarter watt resistor. Let me just check that one more time again. Quarter watt resistor also, because that's only 60 milliwatts. So we can use quarter watt resistors for all this, a 2N3904 here, and we'll have to use a tip 41C for here. Okay, let's get this built now and see how this works. What I'm trying to do here is just see if I can get the output voltage close to 5 volts, and then when I put the motor across there, that to see how much it drops and how much regulation we have here. The amount that drops, that's where my circuitry is going to come in that I'm going to design to cause this here to pick up again and to increase the voltage. And that's going to be later on. But right now I just want to get this voltage regulator built now so I have something to work with for my circuitry. Okay, let's get this built now. Okay, I have my Zener diode, 3 volt Zener. Get my tip 41C transistor. Then I need 270 ohms for the base resistor. 270 ohms, 470 ohms, and 160 ohms. Alright, that takes care of those. Okay, let's build it. Okay. Base collector emitter. The base resistor is 270 ohms. That will go from base to collector. Base to collector here. This is the emitter on this side to the right. And then we go from the collector, we'll use a jumper. These are 0 ohm resistors here. That will be from the collector. That will go to our motor, or that will go to our supply voltage. Okay, so we have the base to collector, 270 ohms, collector to supply voltage. We have the emitter, another 0 ohm jumper here, and that will be to the motor. Put that on here like this. Okay. So now we have our emitter, our collector to base, and the collector to the supply. Now the 2N3904 transistor, which is the feedback transistor. And we'll put that right here for right now. Okay, put the transistor here. Emitter, base, collector. I have this resistor set up here now back here so that I can take the collector through a jumper into the base terminal. So we'll just do that right now. We'll go from the collector of the 2N394 feedback, and we'll take that into the base of the series transistor so that we use that to bring about the regulation. Alright. Now the emitter, left hand side here, that gets the Zener diode from ground to the emitter. Ground being this top here being ground into the emitter. And so now we need to get the divider resistors for the feedback transistor. And that would be the 160. That's 160 from ground to base. And then from base to the emitter output will be the divider there. So then we take another jumper back to the emitter now of this series pass transistor, which is the output voltage. And so now we have the output voltage connected to the base through the 160 ohm resistor. Put that backwards, 160 ohm resistor. And then from there we have our 470 ohm resistor to ground to form our voltage divider at the base of this transistor here. Now let's take some measurements, voltage measurements now. What we're going to do is we're going to turn on our supply voltage, and we're going to bring that up to 10 volts. Okay, that's our supply voltage coming in 10 volts. That's the voltage coming in to the series pass transistor, which we have over here. Now we're going to take a voltage measurement at the emitter of the series pass transistor, and see if we get close to 5 volts. Yeah, our emitter, our series pass transistor, and we're at 9 volts, which we don't want. Okay, I see why the collector is not connected to the base, which is right there. Now we're connected to the base of the series pass transistor. Okay, we're at 10 volts supply voltage. Now we move it to our output here, voltage here. Okay, and there's our output voltage, 4.49. So at least we're better than 9 volts before. The transistor was saturated before. Okay, so now we have some regulation going on here, or I should say we have the proper voltage output that we're looking for. I can adjust these resistors here at the base of the feedback transistor to get this to 5 volts, but we're just going to work right now at 4.9 volts, 4.9 volts, 4.5 volts, just for demonstration purposes. Okay, so what I'm going to do now is I'm going to put the motor across this and see how much that drops down to now. But the regulator is now working properly, and that's the main thing. And so let's put the motor across now. I don't know if you can hear it or not, but the motor's running. Okay, there's the motor running. I'm going to now check the voltage across the motor. I have the probe here to ground. Here's the output, and here's the motor output right here. I'll touch that to there. 4.49. Go back to here again. Here's the voltage across the motor. Here again, you get that under better. Hold it there now, better. Okay. Now I'm going to remove this, and I'm going to put this over here now. So what I'm going to do is I'm going to hook this to the output here, and then we will hook the motor up and see how much that drops. That'd be a better way of doing it. I have the probe here now hooked to the output of the voltage regulator, and we're at 4.48 volts. The motor is not yet running. Okay, I got the wire off. I'm now going to hook the wire to the output. You can see that the motor is running now. Alright, and we have good regulation. The motor is running. Okay, the motor's running, and we're at 4.48 volts. Alright, so now I'm going to remove the motor. 4.47, 4.48, so we are getting regulation, very good regulation. When I hook the motor up, it goes back up a little bit. So it is regulating really nice. Now, that regulates really nice that my circuit that I'm going to put in there to make this work as a torque converter would not be needed under this condition here, but let me work on this better here, because I want to stall the motor now. That's what I want to do. So as I stall the motor now, it drops to 4.46. I let the motor come back on again. Wow, that's got real good regulation. I stall the motor. Alright, ready? Here's 4.46. Stall the motor. It's got very good regulation. So what it looks like is I'm going to have to make the circuit a little bit different so that when I stall the motor, it drops, so that I can make a circuit that makes it come back up again in order to make this demonstration work, because this is just working too good right now as a voltage regulator. So I think what I will do is I will just use this video as a demonstration of a transistor voltage regulator, and I will have to come up with a different circuit that will allow me to demonstrate the torque inverter that I want to design for a voltage regulator, because this is just working really good as it's just a simple voltage regulator, period. I mean, I'm at 4.46 volts with the motor running. I stall the motor, and the voltage doesn't drop across the motor. I mean, it's just, it's just working good as a transistor regulator. So, okay, so this is a transistor voltage regulator with series feedback. That's the schematic for it. And when I come up with a different circuit that will require me to make a torque inverter so I can make the voltage regulator have a feedback from the motor stall current so that I can increase in voltage, I'll make another video. So we'll just use this as a demonstration of a transistor voltage regulator. Okay, so thanks for watching, and that's it for now. Bye. Okay, just let me show you again that how this is working as a voltage regulator. When I stall the motor, it stays at 4.4 volts. Okay, fine. If I take the series feedback transistor out of the circuit, I'm going to disconnect the Zener diode to take all this out of the circuit. So I take all this out now, and so now we're running full force. I put the series back in there again, and now we're back to normal again. Okay, so that demonstrates again how this is working as a voltage regulator for a transistor circuit. Okay, now I think this video is completed in this demonstration, and stay tuned for the next segment on making a torque converter for my lathe coming up sometime here. Okay, bye.